And we are back. Okay, so a couple classes ago we talked about precision. And in chemistry, how we measure precision is by measuring the number of significant figures, or we call them sig figs. And what sig figs are is essentially the number of digits in a number. Remember, we already talked about how saying that like 2 centimeters versus 2.0 centimeters, that means something different. The 2.0 is more precise than saying just 2 centimeters. And when counting sig figs, the most important number is 0 that determines how many sig figs are in a given number. So first off, any non-zero integer, so 1 through 9, those are always significant. So if we have the number 3,456, all of those numbers, 3, 4, 5, and 6, are non-zero. So each of those count as significant figures. So that number has 4 sig figs. So any number without a 0, all you simply do is count the number of digits, and that is the number of sig figs. Now, it becomes a little trickier when zeros come into play, because there are different types of zeros, and for our purposes, there are 3 different types of zeros. First off, leading zeros, that means zeros that precede all the non-zero digits, or essentially leading zeros are just zeros at the front of the number. So the only time you will see zeros at the front of a number, anytime you'll see leading zeros, are decimals that are less than 1. Okay, and these do not count as significant figures. They do not count as sig figs. These zeros simply indicate the position of the decimal point. So 0.0048, only the 4 and the 8 count as significant figures. Same thing if you have 0.532. This 0 is just determining where that, or indicating where the decimal point is. So the significant figures in this number are just the 5, 3, and 2. So this number has 3 sig figs, or I might abbreviate it SF. Or something, even if there are many zeros at the beginning of the number, so like 0.00007. So all of these first 5 zeros, they are all leading zeros. There's zeros at the front of the number, so 0.00007 has just 1 sig fig. Okay, so leading zeros do not count as significant figures. However, captive zeros, and they are called captive zeros because they're held captive, or they're between 2 non-zero digits. And these always count as significant figures. So this 0 here, it's between the 6 and the 7. It's captive, it's between 2 non-zero digits, so therefore all 4 of these digits count as sig figs. So that number has 4 sig figs. Also, it does not matter if there are multiple zeros in the middle of the number. So let's say you have 5,003. Even though this 0 right here is between a 0 and a 5, still in general, it is between 2 non-zero numbers. It's still between the 5 and the 3. And same thing for this 0, it's still, in general, between the 3 on the right and the 5 on the left. So both of these zeros are captive zeros, so they both count as sig figs. So 5,003 also has 4 sig figs. And it also does not matter if there is a decimal point in the middle. So let's say we have 6.0004. So all of these zeros are captive. They're still between the 6 and the 4. So therefore, all of these digits are significant. So 6.0004 has 5 sig figs. Okay, so the second type of zero, captive zeros, zeros in the middle of a number between 2 non-zero numbers, are significant. Now the last type of zeros are the most tricky because sometimes they are significant and sometimes they are not. So trailing zeros, zeros at the right end of the number, meaning zeros at the end of the number, these are only significant if the number contains a decimal point. So 9.300, these trailing zeros, these zeros at the end, they do count because there is a decimal point. So all four of these digits are significant. So 9.300 has 4 sig figs. The reason why we count those zeros in this case as significant is because they add to the precision of the number. So remember, 9.300 is different than saying just 9.3. 9.300 is more significant than just 9.3. Okay, now 150, this is a trailing zero, it's a zero at the end. However, there is no decimal here, meaning this zero is not significant. It is not adding to the precision of the number. So here, 150 with no decimal point has just 2 sig figs. The reason for it, that final zero doesn't add any precision. So when we're saying 150, we could be saying anywhere between 145 and 154. Now, if we were to write the number 150 like this with a decimal point, like this, that means now this trailing zero at the end, now there is a decimal point here, meaning now that zero is significant. So 150 with a decimal would have 3 sig figs. And if you kept on going, if it was 150.0, so both of these trailing zeros are significant since this number contains a decimal point. So 150.0 would contain 4 sig figs. And also, a number like 100 with no decimal point, these zeros at the end are not significant, there is no decimal point, so this would have 1 sig fig. Then, if we were to add a decimal, 100 with a decimal, now, with a decimal, now, when there is a decimal here, finally, when there is a decimal here, now, those zeros are significant because they're at the end with a decimal point. Now, that number has 3 sig figs. Now, the tricky part here is, let's say I asked you to write 100 with 2 sig figs. And we're going to get back to that in 1 second. So, with zeros, there's 3 different types of zeros. Leading zeros at the front of the number, those are not significant. Captive zeros in the middle of 2 non-zero numbers are always significant, and then trailing zeros are significant if there is a decimal point after that number. Okay, then the final rule with sig figs is you're assuming exact numbers have an infinite number of significant figures, so anything not measured in lab. And so something like this, 1 inch is equal to 2.54 centimeters. We would call this a conversion factor. And any exact number that you exactly count, like there are 9 pencils on the table, you assume that has an infinite number of sig figs. So you're essentially ignoring those number of sig figs. And later on we're going to talk about, or today we talked about the metric system and how 1 meter is equivalent to 1 centimeters with all those different prefixes used in the metric system. So all of these conversion factors, we assume when we're using these have infinite number of sig figs. So you ignore them when doing any calculations. And sometimes here, as I said before, sometimes it's easier to put a number in exponential or scientific notation. One, because it's easier to see the number of sig figs. That's easily indicated. And simply, you can write any number with fewer zeros. And so 300 with a decimal would be written as 3.00 times 10 to the second, because with 300 with a decimal, that's 3 sig figs. So therefore, in our answer with scientific notation, we also need 3 sig figs. However, coming back to the example that I said before, let's say we want to write 100 with 2 sig figs. So here, as written, it has 1 decimal, but then when we add a decimal, now it has 3 sig figs. So the only way to write the number 100 with 2 sig figs is to write it in scientific or exponential notation, where we put it 1.0 times 10 to the second. And everyone should understand and be able to manipulate and convert numbers in standard notation to scientific notation and vice versa. And so with this second point, the fact that fewer zeros are needed, so let's say we have the number 0.000058. So we know all of these leading zeros are not significant. So in this number, there are just 2 sig figs, and if we wanted to write this in scientific notation, it would just be 5.8 times 10 to the, and then count the decimal places, 1, 2, 3, 4, 5, times 10 to the negative fifth. So obviously it's much easier to write this number in scientific notation rather than writing out all those zeros. So scientific notation is useful for numbers that are very small or for numbers that are quite large. So with this number, 420,000, instead of writing out all those zeros, you count over 1, 2, 3, 4, 5. This would be 4.2 times 10 to the fifth. And we write 4.2 because all of these trailing zeros are at the end of the number, and there is no decimal point in that number. So it has just 2 sig figs. So in your answer, in scientific notation, you just indicate that there are 2 sig figs. Okay, so that's how we count the number of sig figs in a given number. And now we have to think about how we would use these in mathematical operations. So first off, the rules for multiplication and division are the same. With multiplication and division, you're just looking at the number of sig figs in the least precise measurement. Okay? And that number of sig figs in the answer is the same as that least precise measurement. So, if we look at these two numbers here, 1.342 times 5.5. 1.342, all those are non-zero numbers, it has 4 sig figs. 5.5, both of those are non-zero numbers, that has 2 sig figs. So, that means in our answer can only have 2 sig figs. So when you calculate that out on your calculator, you get 7.381. So now we look at that next number. If it is 5 or greater, you round up. But if it is less than 5, if it is 4 or less, you round down. So since this number is an 8, we round up to 7.4. So that is our correct answer with the correct number of significant figures. So it's the same thing with division. So let's say we have 5.8 divided by 1.71. So here we have 2 sig figs and 3 sig figs. So before you do anything on your calculator, you should know already, okay, my final answer should only have 2 sig figs. Okay, and then finally you do the calculation. You get an answer of 3.3918. And so now you know, okay, I have to round this. And since the next number in line is greater than 5, we have to round up to 3.4. Okay, and it's also tricky here. Let's say we have another problem with multiplication, 2.3 times 4.57. So we know here 2 sig figs, 3 sig figs. We know our answer has to be 2 sig figs here. So when we write this out, so we know we have 2 sig figs here and 3 sig figs. Our answer has to be in 2 sig figs. And when we get our answer, it's 10.35. So we look at the next number. It is a 3. So this number rounds down. So it rounds down to 10. However, when we write our final answer here, we can't just write 10 because we want 2 significant figures. We need to make sure that we add a decimal point. Okay, so with multiplication and division, you're just looking at all the numbers in the problem. Whichever one has the least number of significant figures, that answer has to be the same. Okay, so multiplication and division I think are a bit easier than addition and subtraction. So the main thing with addition and subtraction, you are not counting sig figs like you are for multiplication and division. You're just looking at the least precise measurement, which is measured by the number of decimal places. So you're just counting the number of digits to the right of the decimal point. Okay, so here in this calculation, 23.445, all you're doing, okay, there are 3 digits to the right of the decimal point here. In 7.83, there are 2 digits to the right of the decimal point here. So comparing these two numbers, 7.83 is less precise. So that means in our answer, we can only have 2 digits to the right of the decimal point. So we look at this number, 31.275. That next number after that, it's 5 or greater. That makes it round up. So our corrected answer with the correct number of sig figs is 31.28. So notice here, when adding, all I'm doing is counting the number of digits to the right of the decimal point. I am not counting all the number of sig figs in each number. And it is the same for subtraction. And anytime you are adding or subtracting, I want you to do it this old school method, because if you don't, if you just write it horizontally on a piece of paper, you are liable to make a mistake. So make sure for each of these, line up the decimal points, so it's easy to count the number of digits to the right of the decimal point. So here, 42.2, that has 1 digit to the right of the decimal point. 27.56 has 2, so that means in our answer, we can only have 1 digit to the right of our decimal point. So now we subtract this out, we get an answer, an original answer of 14.64. Now we look at the next number there, 4. That means this number rounds down. So that means our final answer here is 14.6. All right, that's all for today. See you next time.